right, so now we're going to do our derivation of a very important result in time-dependent perturbation theory. And the statement of the problem is relatively straightforward. If we have an initial state, we want to know what's the probability that it will transfer at a given time into a subset of other states that actually are characterized by a continuum of levels. Okay, and so this is going to be a little bit unusual. Most of the background that students have in quantum chemistry is limited to discrete states because they're very common in bound systems to be discrete. We want to loosen that a tiny bit because many times you'll have the ability to make a transition to levels that are, say, so close together that they might as well be continuous. Continuous eigenstates, or any set of eigenvectors that have a continuous spectrum, so to speak, meaning the eigenvalues are not discrete values but are continuous, is a little bit complicated. And the reason why it can be a little bit complicated is because one of our main tools in dealing with eigenstates or eigenvectors is orthogonality. We're used to thinking of orthogonality like this. When j and k, the index, are not equal to each other, we get a 0, and when they are equal to each other, we get a 1. But that only works if they're discrete, right? If they're not discrete, if they're continuous, then you have a problem, because the probability of getting any one index is 0, right? Just like the probability of having any exact value of a continuous distribution is always 0, because you have a probability density, you integrate it from one point to the same point, the integral is obviously 0. So when you have a discrete spectrum, orthogonality is very straightforward. When you have a continuous spectrum, it's less so. All right, so here we have our Hamiltonian, H0, and we're going to presume, nevertheless, that it has an eigenspectrum, just like you would expect if it was discrete, but where these energy values are continuous. All right, what are some operators that we usually assume or usually associate with continuous eigenspectrum? The most obvious one would be position, momentum, or position, right? If you have a momentum, there's not like discrete values of momentum. There's not discrete values of position. So you could have, for example, the position operator. Maybe I'll put a caret just so that people remember this is an operator. And it has an eigenvector, meaning a definite value of position, with eigenvalue, that value of position, operating on itself again. So that would be an example of an eigenvalue, eigenvector, the eigenvalue problem for the position operator. There's one for the momentum operator and any other operator. And so the position operator is going to have positions. They're just, when you say a system is in an eigenvector of the position operator, what you mean is you've localized it. Now, what you know in the next instant of time, because it's so highly localized, it's going to spread dramatically, because position absolutely does not commute with the Hamiltonian. So you will have then instantly a superposition of states later on. And in fact, this is one way you can formulate things like the Heisenberg uncertainty principle. You don't have to. The better way to do it is just to remember about the commutator. But if you want to generate position translation, like move something in space, well, you do it with an operator that's exponential in the momentum. Because in quantum mechanics, a generator is a generator of translation in one degree of freedom is made by an exponential operator in the complementary operator, which like the one that doesn't commute with it. All right, so we won't probably spend a whole lot of time talking about continuous eigenspectra. It is a little bit complicated, but it is obviously an important thing that happens. If you were doing things like scattering, or that's probably the most common place where you see this, then you would do lots of things where you consider what happens with continuous spectra. All right, so how do we deal with this? We deal with the orthogonality in the following way. we imagine that we take the scalar product between two states, B and B primed. And like you would have here, the two different states of, or different eigenstates of position are also orthogonal. And the way to think about that is imagine that they're localized somehow, right? And as long as they don't overlap, then they will be different. Like if I have two Gaussians, one here and one here. So the way Dirac dealt with this was to invent a new function. It's called the Dirac delta function, I guess you would say, the Dirac delta function. The mathematicians insist that you call it a distribution, but nevertheless, it's a function. Now, it has some weird properties. One property is that the Dirac function has an infinite amplitude. Okay, and that means it has an infinite amplitude, but it has a finite integral, meaning its integral is 1 if you integrate over the delta function. All right, so it's very easy to deal with when it's in an integral. It's much less easy to deal with mathematically when it's not in an integral, right? And so that's why we don't typically draw like eigenfunctions of the position operator, because they would be basically Dirac type functions. Nevertheless, this is the idea. So we can associate with this scalar product a Dirac function like this. Now, Dirac functions are even, which means you can switch the order of this. That's no problem. There's another amazing property of a Dirac function, which is that if you have a function of the variable, whatever it is, let's say x, and then you have the Dirac function x minus a, so it's a Dirac function located at x equals a, you're integrating with respect to dx. As long as the integral range covers this delta function, then this will equal the value of the function at x equals a, so f of a. But I'm just reminding you that's f equals a. That's an amazing property and very, very convenient property of the delta function, and that's why you'll see this come back a lot when we look at ultrafast spectroscopy, because many of the integrals that could be very, very cumbersome become much simpler when we pretend that our pulses are delta functions, because we'll be doing these kinds of integrals. It greatly simplifies by simply changing the variable's argument to this position here. All right, so this would be a perfectly good use or definition of the scalar product or representation of the scalar product for a continuous eigenspectrum like this. But we do need to keep track of one thing, and that is that there could be a degeneracy. Right? There could be degeneracy. And the way we keep track of the degeneracy is we simply say, we put it into a denominator here. We haven't said anything about the dimensionality of this problem. If it was a two-dimensional problem, it might very well have degeneracy. Remember what happens with a two-dimensional harmonic oscillator, uncoupled. If they're the two identical oscillators, then the first excited state has 2, second excited has 3, and then 5, and so on. So each of these would have n, for example, 0, 1, 2, 3, and 3 would equal 5, and 2 would equal 3, and 1 would equal 2, and 0 would equal 1. All right, so we're just keeping in track of the fact that there's a degeneracy, potential degeneracy, that we need to keep track of, right? Because we can't tell when we just look at the energy value, whether it's how many states have that energy value. But we, in principle, could know that from this problem here. Okay, so we certainly know that NB is greater than 0. It's either 1 or bigger, it can't be less than 1. And it's the number of states with the quantum number B. Okay. Now what we want to do is define a projection operator. We've talked about projection operators before. A projection operator formally is just one that's equal to itself squared. What it does is when you operate with a projection operator onto a vector, you get back the vector that is aligned along the axis that projection operator projects onto. All right, and so when we have a discrete system, a discrete state, we would have, for example, phi n. That would be like, let's say, the projector onto the state n, right? That's an ideal, exactly like that. Here, we have these continuous states because we want to be able to consider that our initial state goes into a continuum. So we can define a projector onto a capital B, and capital B is going to be this region here, right? The region of states in the vicinity of the energy value EB. So that's not too hard to figure out what you'll do. Remember that we have these continuous spectrums. We can't really do a projector onto one state, right? To projector onto one thing out of a continuous distribution, again, will be equal to 0, just like anything else. But we can project onto a subset. So that's what this is going to be. So we simply integrate over that region of energy B to capture the substate that we have. And then we're going to integrate, just like we had before, the projector, but we're going to include into that the possibility that there's degeneracy. Remember, B, the quantum number, is actually a continuous parameter now, so we can integrate over this continuous, essentially, function. All right, so it still looks like what we had before. If we wanted to have a projector onto a submanifold, for example, of discrete states, we could simply have done this, like this. We could have done that. Then that would be a couple different, however many we had. Here we're just making it into an integral because it's continuous. Then we could also put into here something to do with the degeneracy as well. The degeneracy is going to be important because we want to be able to count states. We want to be able to, at the end, cast all of this in terms of something about how many states there are per unit energy. That's going to turn out to be very important. That's called the density of states. All right, so what we're going to do is we're going to change the variable. So instead of integrating over the quantum number, we're going to integrate over the energy value. That's not a big deal. That's just a sort of a simple mapping, right? If you can add up all the values over B, you can certainly add up all the values over the energy. Okay, so that's what we're going to do there. And we're just going to use this sort of transformation, which is to say this NB dB sort of, let's say, almost like volume element, or this thing here. This is the number of states B in the infinitesimally small region of energy, or of quantum state space B. This will be equal to something over the small energy range, right? We want this to be in sort of energy per index, or number of states, per index. We want this to be equal to something else. So if we have energy now, then it's going to be number of states per energy, because we want, at the end of the day, we get number of states. And here we're going to have number of states as well. But if we're writing it as something times energy, this has to be inverse energy. So it has to be number of states per energy. So we'll call that rho. And then I want to remind ourselves that it's the B, it's the rho of the rho near B. Okay, so near B. Why do I need to be so nitpicky about this? Molecules and most quantum systems will have densities of states that actually depend on the energy level that you're in, just like this, right? The density of states in this one, right, is like 5 times bigger than density. Now, it's a little silly to talk about density of states for continuous things, but certainly it's higher than that. So we want to be able to keep track of the local density of states in the vicinity of a particular energy level, or in a region. Okay, so what we can do then is we can rewrite this equation like this. okay, in that way. All right, and then B, instead of being in the vicinity of, in the region of state space, as it were, of index space, now it's B in the sense of being in the energy space. But we were kind of writing those things interchangeably up here anyway. Okay, so what we're going to do now is ask the probability of making a transition. This is, remember, the projector onto the subspace B, right? And I want you to remember way back to when we asked about things like the probability of ending up in a particular state, all right? So what we could do is we could say, imagine we start in the state A and we go to the state B in time, right? How do we do that? We started with the state A, so I'm just going to call it A. We evolve forward in time with the time evolution operator. So I'll just call it T here. Right? And then we asked, what's the probability that we're in the state B now? And then we square that. Right? This is something we did very early on in the class at the very beginning. It's basically a postulate. Well, let's expand this. Let's take this and then flip it around and move it over here. So if we do that, what do we have? So we're going to flip this around. So we have A, U dagger, B, B, U, A. So what do we see here? We see the state at time t, and it's amazing, but it turns out that this transition probability is nothing other than the expectation value of PB. That's pretty cool, isn't it? That's why we messed around with all this. So all we have to do is compute the expectation value of PB using the state vector that we evolve with the perturbation theory Hamiltonian, or time evolution operator, sorry. And then we will have the transition probability to that order in the perturbation. Obviously, we need something to connect these two. All right, so let's work that out. We're gonna use the first order term, of course, because that's what we're doing. I'll see how far I can get and keep us on the same board here. Okay, so we simply put this in, and we're gonna have W, and we're gonna call it A goes to capital B, meaning we're starting in a particular state A, and we're going to go to the region of B, which could be multiple states, right? Okay, and so that's going to be, like I just said, A, U dagger, we'll just use T naught equals 0, PB, this object here, U, T0, and then A again. It's this expectation value which is equal to this transition probability. Okay, so we can just substitute in and we're good to go. So we're going to integrate over B energies in the region around B, whatever that happens to be. All right, and then we plug in this equation here. Plug it into this equation here. This is going to be all the stuff. And if you can move this around, this is just a function. So it slides in the Tetris style. So the most useful way to do this is A, U dagger of T, B, rho B of E, the continuous density of states near the B energy, B, U, T0, A. All right. Now, we did this before, right? This function here was the whole story of what we did in the last example, when we had a continuous perturbation that was on, for a certain amount of time. Instead of A goes to B, it was J goes to K. We substituted in the first order expression for the time evolution operator. Then we got this, integral function, this f function. Okay, so we're going to use that fact again. What can we do? So we see not only that, we see that this term here and this term here are what? How are they related to each other? Well, these are complex conjugates of each other, right? So it really is exactly what we had from the last time, right? So this is going to be that f function, the coupling term squared divided by h bar squared. All right, so let's just remember that. The only thing we have to add is this bit here. So I want to make sure I don't go too quickly because this could get, I don't want anyone to get lost here, but I want you to fully understand that these two terms, when multiplied together, are exactly W, A goes to B, that we worked out just a minute ago, or just a lecture segment ago. All right, and we know what that is, so we're going to plug that in. So B and E, all right? So we have the, by the way, I've been sometimes forgetting to put energy, volume elements. So it's over dE, of course. We're integrating over energy. So I'll put it at the beginning to remind myself. Integrating over energy. So what is WAB? It's the coupling between the two states. VAB. Actually, sorry. Remember the order? It was J goes to K. It was actually H primed KJ. So BA squared. Yes, we are assuming, of course, that there's a constant coupling. The Hamiltonian for this whole thing is exactly the same. It's H naught plus, in this case, V, for example. All right, divided by H squared. Sorry, H bar squared. And then the F function. T omega BA. And then what's the new bit? Is that we're simply integrating this transition probability from one state to another state over the density of states of the final state. In some sense, you could have just written this down. And I'm sure that that's got to be how Fermi figured this out. He just said, well, you have one state to another state. Let me just treat every one of these like separate processes. And then we'll just integrate the whole thing at the end, right? So the only thing that you do here is you make it quite formal. You make this, you use the projector operator, you make the expectation value of the projector operator, and then you don't have to be quite as insightful. You simply follow the rules, which is what we did here. All right, and did we make any approximations? Not a whole heck of a lot, right? First order perturbation theory, of course, that there's a region that we're constraining to. Why are we doing that? This is why we're doing that. Remember what we found from this previously. This is a sharply peaked, this could be a sharply peaked function as a function of energy gap. And now what's the energy gap? The energy gap is between A and each of these states. So what about this state down here? Well, it would have like this energy or that energy, depending whether it's lower or higher. It's omega BA, okay? BA means B minus A. So the final state minus the lower state, initial state, if that's positive, that means we went uphill. So that would be here, uphill. And this is downhill. This is as a function of omega BA. And this is this F function. All right, so that's the important thing. This function is generally speaking compact in general, right? And that's going to allow us essentially to replace this integral with like the average value of the function in this region. That's kind of an important math piece. All right, and we know that this function is peaked nearby the minimum, where omega BA is approximately 0. What does that mean? It just means that you don't change the energy all that much. You shouldn't. There's no source of energy here, right? We have no energy. We're not adding energy. We have this coupling, but other than that, nothing. So if you want to conserve energy, you better end up in a state that's pretty close to the energy you started in.